deploy a major new system update to production, and suddenly your stable architecture starts experiencing cascading localized blackouts. Your engineering team takes an existing, reliable prompt and migrates it to a newer, highly capable language model. Instead of an immediate performance boost, the evaluation suite lights up red. The new model fails on edge cases that the older generation handled with ease. The standard developer reflex is to blame the upgrade. We assume the new model lacks the necessary capability, is behaving erratically, or requires us to rewrite our instructions using capital letters and exclamation marks. But the new model is not failing. It is actually executing flawed legacy instructions with much higher fidelity than its predecessor. To see exactly how this happens, we are going to debug a failing production customer support bot named Meridian Mobile. Transitioning from reactive tweaking to deterministic prompt debugging requires there's isolating specific failures, identifying the prompt anti-pattern, and applying structural fixes. Our first failing test case involves a user on a grandfathered plan asking the bot for their exact hotspot data limit. This split screen shows the customer context payload on the left explicitly states they have 5 gigabytes of hotspot data. Yet the model's output on the right ignores this, deflecting the user to a generic URL to check their plan. This is not a hallucination. The model has the data. It is actively withholding information. We can trace this behavior directly back to the source prompt. Hidden in the instructions is a strict directive. Never give a customer the wrong plan details. Instead, point them to the URL. This is a defensive patch. It was likely introduced many months ago to stop an older, less capable model from guessing incorrect plan details and quoting the wrong prices. Modern models possess superior instruction following capabilities, which causes them to overfit to this defensive caution. The model prioritizes the rule of never giving wrong details over actually answering the user, even when the correct data is in its context window. The solution is to delete the rigid patch. We replace it with an instruction to provide a balanced view based strictly on the provided customer context variables. Defensive prompt patches written for older generations act as toxic, technical debt. They actively degrade the performance of highly obedient models. Our second failing test case occurs when a user asks what their next bill will be if they upgrade their plan mid-month. This task requires precise proration math calculations. Looking at the output in the terminal, the model attempts to reason through the problem, generating a dense block of text, but it completely fails to provide a concrete mathematical total. Returning to the system prompt, we find the cause. Critical always calculates any prorated amounts correctly. This is the instruction fallacy. Capitalizing words or adding critical does not change a model's underlying architecture or its ability to perform arithmetic. Demanding a language model perform complex internal mental math through semantic pressure is a structural failure on the developer's part. Instructions do not create capabilities. We apply a structural fix. We strip out the emphatic instruction entirely and define a discrete API function, seamlessly routing the numerical variables to it. Mathematical logic to an external calculator gives the model the actual tool it needs to succeed, rather than relying on predictive text generation to stumble upon the right number. Deterministic outcomes for complex tasks require bridging capability gaps through external tool calling, not just aggressive word choice. The final failure mode happens when a user reports a direct billing conflict. Instead of escalating to a human agent, the model attempts a dangerous self-diagnosis. In the code snippet governing escalations, we find the instruction, avoid escalating or transferring to a care specialist as it costs approximately $8. Highly obedient models will read this constraint and aggressively optimize for it. It sees a penalty for transferring the user, so it does everything in its power to avoid that penalty. Stating only the cost of an action without stating the cost of inaction creates a pathological bias. To correct this, we introduce the counterweight. Failing to resolve the issue correctly costs a refund and destroys customer trust. The engineer must explicitly state the full constraint matrix. By providing both sides of the business logic, you give the agent the parameters to evaluate the actual risk. Once the complete reality of the business trade-off is exposed in the prompt, the model's escalation behavior immediately normalizes, transferring the user when appropriate. Because advanced language models possess nuanced trade-off analysis capabilities, engineers must present the complete matrix of business heuristics to prevent the model from over-indexing on isolated rules. During this debugging session, we applied 3 distinct structural fixes: removing legacy patches, introducing API tool schemas, and balancing trade-off logic. The cumulative result of this systematic process is a clean evaluation suite. The failing test case is clear, proving the prompt is now operating deterministically. Migrating to a highly intelligent model requires a strict revision of how we maintain and scale prompts. Developers must stop treating prompts as dumping grounds for reactive behavioral band-aids. By shifting engineering focus from semantic pressure to structural design, production prompts evolve from fragile text documents into rigorous, scalable systems.